Today we are going to talk about a new optimization technique, Eagle Perching Optimizer, a model-free global optimizer. This technique is presented by Amir Temur Khan, which is myself, with the supervision of Dr. Shwiley. Have you guys ever wondered that how Eagle make a flight or locate its destination while moving up in sky? Look at this picture. As you can see, the eagle is flying in a hilly area. So whenever eagle wants to perch on the peak of an area with mountains, it usually glances around a big area by sampling a few points. And within that point, it will look for the tallest one and will move there. When it arrives there, it will again glance the area. But this time, the glancing angle is small, as you can see in the picture. Again, it will sample the area and look for the tallest point. So this is a continuum process by incrementally scaling down the scanned area and recursively finding the taller point until it reaches the tallest point within its surrounding. To make the motivation more clear to you guys, let me walk you through the simple steps that this algorithm involves. Look at this picture. An eagle is flying around in a hilly area and is in search of a tallest peak. So what it will do, it will glance around and will sample the area. The red dots here represent the sampling points or the sampled area. Now it will look for the tallest point within those samples and will move toward that point and will reside there. Once it reaches there, now it will again sample the area, but this time the sampling area will be far less than what it was earlier. As you can see here, now the samples are within a confined range. Now, within that range, it will again look for the tallest point and will fly to that point, as you can see. And the same process will repeat over and over again until it reaches to the maximum or the peak point within that area. So far, so good. To this point, we have discussed the nature of the eagle and how it locates the highest point of the ground while flying up in the sky. And we also went through different recursive processes that are involved in making that happen. But for the mathematical formalization, there are like two main questions that we need to ask. Number one is that how are we going to formulate the algorithm for higher dimensions? And the second question is that how are we going to engineer the algorithm more effectively or like make it more useful? Before diving into its MATLAB code, which will obviously make things complex, let's just keep it simple, and first we will walk through the pseudocode that how we manipulated the eagle perching nature into something useful as an optimization technique. So the algorithm has got total 10 steps. Let's say we have a function f and we want to evaluate the highest point or the value that function can have. So the first step says that we need to initialize a variable x with a random value, and at that point we will calculate the value of function. In second step, we are assuming that the randomly generated point x steric is the best point we can have, and on that point the value of the function is the best function value. So this is our first iteration. The third step is similar to the glancing and the sampling of the eagle. Here we're going to generate n point around the randomly generated x steric, and the formula is straightforward. xi is equal to x steric plus L into random. Here I represents the number of points that we are generating. L is equivalent to the glancing angle of the eagle. At first its value will be high, but with every iteration it will decrease. Rand n here represents the random values that we are generating, but it will also control the number of eagles and the dimensions we are dealing with. Now moving on to the fourth step, which says that evaluate the function value at each sample that we have generated. For fifth step, we're going to look for the highest or largest value of y that we evaluated in step 4. Let's say x steric is that point where y has got the highest value. In sixth step, we're going to compare that value of y with y best. Here y best is the one that we assumed in step 2. So if the condition fulfills, we're going to assign new value to x best. Now this time it is x steric, and y best will be assigned y steric. In step 7, we will reduce the area of searching as we discussed earlier. Here L represents the area or the glancing angle that we will reduce now for the next iteration by the factor ETA. ETA is a value that lies between 0 and 1. In step 8, we will increase the iteration, and in step 9, either we will go back to step 3 and repeat the same process, or we will go to step 10 depending on our iteration condition. If we have met the maximum iteration value, then we'll obviously move to the step 10. And in step 10, whatever the value of x best and y best is there, we have got our highest value of the function. So that's how we can obtain the optimal solution of any function. In this case, we looked for the maxima, but we can apply the same for the minima as well. Now let's just dive into the MATLAB code of EPO algorithm. We have divided the code into different parts, and I will walk you through each part one by one. So first off, we have got the very important variables that we will use in this algorithm. The second part is about intermediate variable, which are not very difficult to understand, so you can do that on your own. So coming back to the main variables, first off, we have got the number of tests, which in this case is assigned to 10. It actually represents the number of time we will run the algorithm. So we are not only testing the algorithm, but we are making a conclusive results by testing that algorithm for a certain amount of time. The second variable is TS. It is simply the number of iterations a single algorithm will go through. The dimensions represent the number of dimensions that we are exploring to get the value, the optimal value of the function. L scale here represents the glancing angle or the area that we are searching in. So at first it has a very high value, but with every iteration the value will decrease eventually. K particles represent the number of eagles that we are using to look for the optimal solution. We have got upper bound, we have got lower bound. RES is a constant that is actually used to evaluate the value of ETA. ETA, as we discussed in the pseudocode, is used to decrease the value of L scale with certain amount. Then we have got F objective function. It is actually a separate function that is used to define a function. Here you can put your function that you want to test. And lastly, we have got x naught. X naught actually the random values that we will generate at the beginning, and we discussed this in the pseudocode as well. X naught is actually an x center, and y center is actually the value of the function on those randomly generated points. So we discussed both these, x center and y center, at the beginning of the pseudocode. The code of the algorithm is super easy to understand. Here you can see we have got two for loops. Number one is the number of times we will test the algorithm, and the second loop actually shows that how many times we will iterate for every single function. So at first we will evaluate the x delta, and here x delta is equals to L into rand, as we discussed in the pseudocode. And as I told you there, that rand function is actually based on the number of particles or eagles that are doing the searching process and the number of dimensions. So here you can see the rand function defines or is based on both of these two things, which also satisfies the matrix condition as well. And here we will simply evaluate the value of x, which we discussed in the pseudocode as well. What it means, we are actually generating n points around the randomly generated x. Once we have n points, we will evaluate the function on each of these points. Here you can see a small for loop. So the small for loop is actually used to iterate through all the particles and calculate the value of y for each point. As we discussed at the last of the pseudocode, that this algorithm can be used for the maximization as well as for minimization. So here we are focusing on minimization. And as you can see here, we are evaluating the minimum value of the n generated y, or n generated values of the function. So y naught here represent the minimum value, and m is actually the index where that value is located. This is a simple check only to make sure that a function doesn't have an infinite value. So x center is now assigned with that point where the function has the minimum value, and y center itself has the value of the function. at this point of the code, we will look whether the y center is less than y min or not. Y min is actually the value of the function that we evaluated at the very beginning of the code, even before starting the EPU algorithm or the iterations. So if the y center is less than y min, then we will reassign values to x min and y min. This time x min will have x center, which is the new value, and the y center is actually the value of the function at x center. So we have now new x min and y min. The last part of this algorithm is the re-evaluation of L scale. As I told you, L scale will decrease eventually on every iteration by the factor ETA. We did this code in two ways. We kept the value of ETA constant for an instance, and then we changes the value of ETA. In other words, we actually decrease the value of ETA as well. I will show you the results of both the cases. But here, to this point, the algorithm actually ends. The later part is actually to test the algorithm, as I said earlier, that we are testing the algorithm for a number of times. So this part is actually for that. We will store all the minimum values of the functions, and we will store the minimum points as well. We will then reassign the value to x center, L scale, and ETA, and we'll repeat the process over and over again until we fulfill our number of tests limit. As we tested this algorithm for a number of times, so it is important to calculate the standard deviation and mean of the function value, as well as the point at which that value of the function exists. So in this part of the code, we evaluated the standard deviation of the function, and within this loop, we calculated the average value of the point where that optimal value exists. Similarly, we calculated the standard deviation of those points. And at last, we calculated the average of the function as well. And finally, we displayed the results. Here in MySQL, you can see we have defined a function, a very simple function. From the definition of the function, you can tell that its minima exists at x is equals to minus 0.5, and the minimum value of the function is 0. So we tested this function with this algorithm, and these are the results we came up with. Here you can see that the standard deviation of the y is 0, and the average value that we got of y is 0. And similarly, the standard deviation of x is 0, and the average value of the y is minus 0.5, as I said earlier. And the two values actually represents the number of dimensions we are exploring in. We tried this algorithm on a number of unimodal and multimodal functions, and there were like two cases. Number one, where the ETA was varying. It was linearly varying from 0.9 to 0.8, and the other case was where ETA was constant. And so here you can see this is the definition of the function, and here this is the calculated or average point where the convergence of the function occurs, and this is the actual point where the convergence needs to occur. So you can see the deviation is very small. Similarly, here is the function value, and here is the actual function value, and you can see the deviation is in the power of minus 61. Similar is the case with ETA constant, but as you can see, the standard deviation here is like large as compared to standard deviation with ETA varying. So with ETA varying, we were able to get more conclusive results than ETA constant, but both of them produce the results just fine. Similarly, we tested this function on algorithm on other functions as well. As you can see, there are like number of functions, and the trend between ETA varying and ETA constant was same. ETA varying produced better results as compared to ETA constant. We compared the working and the efficiency of our algorithm with other renowned algorithms as well, like Dragonfly algorithm, and then Ant line optimizer, particle swarm optimization, and other renowned optimization techniques as well. And we use the same functions, same unimodal and multimodal functions, and the results were very satisfactory. Our algorithm actually produces way better optimal points as compared to Dragonfly or particle swarm optimization. You can see all these results here. We further expanded the horizon of this algorithm to real-world problem as well, which includes some constrained problems. For example, we tested it on cantilever beam design problem, the 3-bar design problem, and the third one was the gear chain design problem. And all these 3 problems are comprehensively discussed and compared with some other renowned algorithm as well in our paper. As I said earlier, that we have a paper on this algorithm as well, and I have included the link here of the paper as well as the MATLAB code. I will further place the links, both these links, in the description as well, so you go and check out the paper and the MATLAB code. And finally, thank you all for listening me.